class. Alon is a postdoc here. He started and he was a student of Shai Shalev-Schwartz at the Hebrew University. And he's done a very interesting work on merit theory and optimization. And today we'll talk about also a very nice work about non-convex optimization and how it applies to generalization field.
Thank you. So I will talk about fast rate for empirical risk minimization of strict order problems. So this is mainly joint work with my PhD advisor Shai Shalev-Schwartz and also with Ran Gilad-Bachar from Microsoft Research. So as we know, most provably solvable problems in machine learning and optimization are convex. Examples consist including SVM, boosting, and regression, but many important ML problems are non-convex. So deep learning is very popular, but also sparse recovery, topic models, dictionary learning, all of these problems are inherently non-convex. And the current effort is to identify alternative appealing properties that allow us to efficiently learn. So non-convex learning problems introduce two challenges, mainly two challenges. One of them is, the first one is multiple local minima, which might be far from being global as opposed to convex optimization. And the second one is existence of saddle points. So in this talk, I will essentially ignore the first challenge from reasons that I will explain later. And we focus on the second challenge. And we will consider a family of functions which have been recently investigated, which are called strict saddle functions. So as the picture shows, strict saddle points are critical points that there are still direction to minimize, to decrease the function from them. They are not minima, they are not local minima. And strict saddle points are strict in the sense that they can be relatively easily distinguished from local minima. And we will define it soon. So the additional assumption, optional assumption that we make is that all local minima are global. And also that there is some symmetry between minima with respect to the loss. So let me explain what I mean. The motivation is that the problems that we focus on are all the strict saddle problems that have been investigated so far have this form of low-rank problems where we minimize over two matrices UV of size D times R. So R is smaller than D. This is the low-rank parameter. And the objective is F of UV transpose plus some regularization term.
It's not the same R. You have R as objective.
No. Yeah, okay, yeah. This is a different R. Sorry, yeah. So the theorem proved in this paper that under some suitable condition, there exists a minimizer of this problem such that all the minima of these problems are equivalent. They are obtained by some rotation matrix R. And so instances of this problem are matrix completion, matrix sensing, or bus PCA. So I say that these assumptions are optional because I will be able also to interpret our results in the absence of these assumptions. Okay, so the recent study has yielded efficient algorithms for minimizing strict saddle problems, either by using second order information and recently also some variants of SGD that converge also to minimizers. And in this talk we talk about generalization, about the statistical cost, and our main theorem is that strict saddle problems are as easy as strongly convex problems. This is the informal statement. Okay, so I will start with the basic setting. So we consider a standard path model where we minimize the expected risk over a set of hypotheses W. F denotes the loss function. The expectation is over the draw of instance Z. So, for example, if in deep neural network, the hypothesis corresponds to weights of the network. And the instances are, for example, images and categories. And F might be the logistic loss. In PCA, W corresponds to projection metrics, and F is the Rayleigh objective. So how do we solve such a problem? The main paradigm is empirical risk minimization, and then we have where we are given a sample and we return the minimizer of the empirical risk. And then we have two main questions. The first one is the computational complexity of solving the ERM, and the second one is the sample complexity. What is the minimal size of a sample for which we are guaranteed that the output of ERM, so the expected risk of this output, is epsilon close to the corresponding empirical risk. So here we focus on the second question, and there are mainly two approaches for establishing bound on the sample complexity. The first one is a combinatorial approach, where we use some combinatorial structure of the hypothesis class, and this typically yields rates which are called slow, in the sense that n scales with 1 over epsilon square. If we want accuracy epsilon, then the sample complexity scales with 1 over epsilon square. The second one is a geometric approach, where we mainly use geometric properties of the objective. And this can give us a fast rate for a well-conditioned objective. And informally, we ask, are strict saddle functions well conditioned in some sense? So here is the precise definition of strict saddle functions. We say that the empirical risk is alpha gamma tau strict saddle if at any point W one of the following conditions hold. So the first possibility is that the gradient is non-vanishing at W, and this is quantified by a parameter tau. So this means that we relatively far from a critical point. The third possibility is that we lie in alpha strongly convex region around minimizer. And the second and the most interesting possibility is that we are near a strict saddle point, and this is quantified by parameter gamma. We require that the minimal eigenvalue of the second derivative is smaller than minus gamma. And we also make standard assumptions such as Lifshitzness and two-sided smoothness. This means that all the absolute value of the eigenvalues of the Hessian are smaller than beta. The main theorem is as follows. If we assume that the empirical risk is alpha gamma tau strict saddle, and this assumption should be made with high probability, then the sample complexity is at most the maximum between these three terms. The first one is rho over tau. So rho is the Lifshitzness, tau is the non-vanishing gradient parameter. Beta over gamma, beta is the smoothness parameter, gamma is the strict saddle parameter. And the third term is 2 rho square over alpha epsilon. So rho again is the Lifshitzness, alpha is strong convexity, and epsilon is the accuracy. So in most cases, we expect that the third term will dominate, because it's the only one where the accuracy appears. And we know that this is a fast rate because the dependence on 1 over epsilon is linear.
So this is generalization, sample complexity for generalization at the global optimum.
So if we assume that all local minima are global, so we assume that the ERM actually achieves a minimizer, and this gives us a global approximation to the global minimum. If we remove this assumption, what we can actually prove is that we don't consider ERM anymore. We consider an algorithm which converges to local minimum, and then the same sample complexity result ensures that we converge to some epsilon approximation of some local minima of the global of the expected risk. This is what you expect, right? that you can converge to epsilon.
The empirical risk and the generalization error that you're converging is the point you converge to. Is it,
You converge to local minimum of the global of the expected risk.
no, but can you say something about the generalization error of that?
Yeah, you converge to some point which has generalization error, which has epsilon close to the some local minimum.
The point you converge to, the empirical performance there is up to epsilon of the, will generalize, will be the same for the for the test set.
No, I mean, if we do not assume that local minima are global,
Yeah.
then you will converge to some local minima. We assume that we are able to converge to some local minima of the empirical risk. And this sample complexity ensures that you get epsilon close to some, to the loss of some local minima of the global risk.
The theorem controls the difference. The theorem controls the difference between train and test.
What do you mean?
What you do here is control the difference.
Yeah.
But not uniformly, only at the local output. Okay.
And can you say so? So let's assume that the expectation of risk is strict saddle. Can you bound the probability that the empirical risk will have the strict saddle?
Okay, so we have another result which I skip in the slides, which assumes that the true risk is alpha gamma tau strict saddle, and then we have nearly the same result with another dependence on the dimension.
Of the parameter space?
Yeah, for the problems that we will discuss here, there is a more direct way to show that, for example, we will consider PCA and we will have direct approach to move from assumption on the distribution to assumption on the empirical risk. But in general, if the true risk is alpha gamma tau strict saddle, then you will have a blow up of size D in the sample complexity, in order to ensure that the empirical risk is also strict saddle. Yeah, linear.
So the empirical risk function is your sum over your samples, right?
Mm-hmm.
So if I fix the number of samples that I have an empirical risk function, and that one might or might not be strict saddle.
Right.
But then you're saying, okay, let's assume that it is strict saddle, then I need this many samples. But you already had the number of samples to define the empirical risk.
Yeah. So in any application, you have the confidence parameter delta. So you need to ensure that with probability 1 minus delta, the strict saddle property holds as well, right? And then the sample complexity result is valid.
So what I don't understand is in what order these things are defined? Because it seems to me that you cannot define the alpha gamma tau strict saddle property of the function before you define the function. So to define the function, you need to know how many samples you have.
Yeah, the sample complexity is usually a function of epsilon, the accuracy, and the delta, the confidence. Okay. So you say that if we want the result to hold with probability 1 minus delta, then the sample complexity is the number of points that are needed. So in any application, you need to bound the number of, given delta, you need to bound the number of samples that are needed to ensure that the strict saddle property holds with this confidence. And, okay?
This property, if it holds for a single example, it's going to hold for an ensemble example.
This?
The alpha, gamma, tau, if it holds for a function, it's going to hold for an average of functions.
Yeah. So, as I said, if you can assume this on the expected risk, and this holds with probability 1, and then you can bound the number of samples that are required in general to ensure that the empirical risk is also strict saddle. And this will give you the same parameters. But in many applications, this gives you, you get more, a better bounds by directly showing, for example, we will show that for PCA, this is the case, that you can prove that for a reasonable sample size which is independent of the dimension, you can guarantee that this holds with high probability. Okay, so the last term is fast rate, as we said, and this is also the rate in the strongly convex case. So this is why I claim that essentially strict saddle problems are as easy as strongly convex problems. Okay, so the outline of the proof is as follows. We start with some background on stability analysis and show that explaining why stability analysis gives fast rate for a strongly convex and Lifshitz objective. And then our proof is essentially a reduction from strict saddle to strongly convex. So algorithmic stability is a property of the learning algorithm. We say that a learning algorithm is stable if a slight change to the input doesn't change the output much. And it is known that this is necessary and sufficient condition for generalization. The definition is we are given a sample, and recall that W8 is the minimizer of the empirical risk. For every I, we consider removing the example xi, and we let W8i be the corresponding minimizer. And then we define delta I to be the difference in the loss between W8i and W8 with respect to Zi. And stability complexity is the minimal size of a sample for which we ensure that delta I is smaller than epsilon for every I. And it is known that stability implies generalization in the sense that the sample complexity is bounded above by the stability complexity. So if we want to achieve a bound on the sample complexity, it's sufficient to obtain an upper bound on the stability complexity. So we say that strong convexity encourages stability, and the picture that gives intuition is this. We look at quadratic function, and we see that if we slightly perturb this function, we obtain a function whose minima is very close to the original one. And the formal argument, by using strong convexity, we can see that the difference in the empirical risk between W8i and W8 is at least alpha over 2 times the squared Euclidean distance between these vectors. And this follows from strong convexity. But since W8i is the minimizer of the risk when we remove example I, then this is the difference in the empirical risk is at most, the difference is at most 1 over n times the distance, the difference in the risk with respect to the ith example, right? And using Lifshitzness, the last term is bounded by rho over n times the Euclidean distance. And by rearranging, we obtain a bound on the Euclidean distance, and using Lifshitzness once again, we obtain this bound that says that the distance, the difference between the loss is bounded by 2 rho square over alpha n. And if we want this to be smaller than epsilon, we obtain that the sample complexity is bounded by 2 rho square over alpha epsilon. So this is the strongly convex case, and our strategy will be to show that if the sample is large enough, we actually, in the strongly convex case, that is all the W8i and the W8 itself lie in strongly convex regions, and therefore the analysis for the strongly convex case apply. So this means that we need actually to exclude the possibilities 1 and 2 for these points, non-vanishing gradient and strict saddle for all these leave one out minimizers. So we want to exclude to show that for a large enough sample, to exclude the possibility of non-vanishing gradient. So we define by G minus I the gradient of the empirical risk when we remove example I.
Question. So the strategy is to show that near local minimizers functions more or less strongly convex, and then you're going to have stability.
Mm-hmm.
But couldn't it be that the change of one example would mean that the optimization would reach another?
Yeah,
It wouldn't even reach the same region.
exactly. So yeah, this might happen, and therefore this is why we assume that all local minima are global, and also there is symmetry between all of these regions.
Symmetry? That's
Yeah.
what we mean, a symmetry point.
And if we remove this assumption, what we can claim is only for average stability. Only in the, I mean, they might be in different regions, and then we can only claim that there is average stability and converges to some local minima. Okay, so so by first order condition, if we evaluate this gradient at W at I, this is 0. And then by using Lifshitzness and the triangle inequality, we observe that the entire gradient, the norm of the entire gradient at W at I, is at most rho over n. So if you want this to be at most tau, then it's sufficient to have n of order rho over tau.
So, Alon, you can exclude these cases 1 and 2 by optimization. So if you apply any optimization algorithm, it's not going to converge to a point that satisfies condition 1 and 2. Instead of imposing a condition on the final point that you reach.
But you look at W at I, and you want that it won't converge. It doesn't see the example Zi. And you want to ensure that W at I doesn't have a non-vanishing gradient with respect to the entire empirical risk, right?
Yeah.
So how can you ensure this just in terms of optimization?
Well, just because, so I think that maybe that's the same argument over here, because it's the average of W is the average of all these. It's very, Wi is close to W.
Mm-hmm.
So,
This is what we,
yes.
yeah.
Okay,
Mm-hmm.
nice. So that's the kind of what, but otherwise, by optimization itself, you ensure that the final W reach doesn't satisfy condition 1 and 2.
Yeah, I mean, W at I is the minimizer of the empirical risk without Zi. So for this, you know by optimization that the gradient is 0. But then you want to consider the additional example and claim that.
Oh, you assume it is 0 even. Okay, fine. So
Yeah, and then when you consider the additional example, it can only increase by additive factor over n.
so you assume exact optimization over.
Yes. Yeah, and also if you assume approximate, it's
Right.
Excluding strict saddle is very similar. We define the second derivative when we remove Zi, and then by second order conditions, evaluating this h minus I at W at I, we obtain a positive semi-definite matrix. By using smoothness and triangle inequality, the minimal eigenvalue of the empirical risk of the Hessian at W at I can decrease only by additive factor minus beta over n. So if we want this to be larger than minus gamma, then n should be larger than beta over gamma. So we conclude that if n is larger than the maximum between these two parameters, all the W at and all the W at I lie in strongly convex regions around minimizers. And as Nadav remarked, they might lie in different strongly convex regions, but as we assume that there is symmetry between these minima, this doesn't matter. We may assume, without loss of generality, that they do belong to the same strongly convex region. So this gives us the final result that the sample complexity is bounded by these three terms. So there is one technicality which we should extend the result to the constraint case. So far we discussed the unconstrained case. So we deal with M equality constraints, and then there is extension of the strict saddle definition to these settings by get out, and we extend our analysis using KKT conditions. As an example, we consider PCA, where we are given endpoints in RD. For simplicity, assume that they belong to the Euclidean ball. And C is the empirical covariance matrix. And the objective is to find the largest eigenvector, minimum of minus V transpose CV, where we require V to have a norm exactly 1. And the lemma says that if we assume that the difference between the leading eigenvalues is larger than some constant G, then PCA is strict saddle with all parameters proportional to G. And as a corollary, we obtain that the sample complexity here is 1 over G epsilon. So if we, instead of assuming this assumption directly on the empirical covariance matrix, we assume this on the true covariance matrix, then by Bernstein inequality, we obtain that with sample complexity of something like log D over G squared, no epsilon there. The same gap appears also in the covariance matrix, in the empirical covariance matrix. So here is an example. We need to consider this sample complexity as well, but as long as G is smaller than, is larger than epsilon, we still obtain an improvement, since the sample complexity in the standard case is 1 over epsilon squared. So here we obtain an example where if we have a gap which is larger than epsilon, we obtain an improvement. The previous proof of this fast rate used the local Rademacher complexity, and here we obtain a more geometric proof of this fact. We have another application to differential privacy. So as we know, in differential privacy, we says that a learning algorithm is differentially private if for any two neighboring samples, this means that I consider a sample and then I consider another sample where xi is removed, and any possible output, the probability for that the learning algorithm will output some point in W is essentially the same, and by this is quantified by exponent raised to the power of epsilon p, which when epsilon p is small, this is the same, almost the same as 1 over epsilon. And the main theorem in this part is that if we assume that the empirical risk is alpha gamma tau strict saddle, then the standard of approach of adding Laplace noise to the ERM, we obtain both epsilon generalization and epsilon p differential privacy, and the sample complexity goes by d over epsilon p. Okay, so as a summary, we have shown that strict saddle problems are as easy as strongly convex problems, and we discussed application to PCA and differential privacy. Thank you.
So you can also prove generalization